Good morning, everybody, and welcome. Hi. Yeah, the plan is just start talking about waves, chapter 11 stuff. I'm working on giving you sort of a practice problem set for this chapter. I haven't posted it yet, but I'm pretty close. The course evaluations have been coming along, so a few of you have done that, so thank you very much if you have already done it. The term test 2 has been mostly marked. I think there's 4 left or something that were found in a box. So, so actually 797 students wrote the test. The average was really great. I was really proud of you guys for that one. Well done on the test. 87 of you got 100% on it, and 42% of the class got either A or A+. So great work. Just to compare, this is what was the test 1 was clearly a little more difficult, or the marks were a bit lower on test 1. But I mean, there was more of you. And this is what the histogram looks like. So this is, again, sort of a bimodal histogram for the top students. I don't really understand that exactly. It was up and then down and then up. And we did see something like that on term test 1 as well. But the median has gone up about a whole letter grade there. Okay. As far as checking it over, I've posted these detailed solutions and videos of me working through the solutions. I've also, just yesterday, posted the marking rubric that was used by the TA who marked all the written problems. But it's pretty much what you'd expect, 2, 2, 2, and 2. You're awarded partial credit for doing correct steps that would get you towards the right answer. You should have received an email from gradescope.ca with a link to the scan of your written question. If you believe that an error was made in the marking of your test, you can submit a remark request through Gradescope, and the deadline for remark requests is 9 a.m. on next Wednesday. And if I receive a remark request, I reserve the right to correct the marking according to the rubric, even if it goes up or down. But I will definitely fix it before the semester's done. Any questions about test 1 stuff? Or sorry, test 2 or test 1? General stuff? I'm around in office hours if you want to talk specifically about your situation. Balconies are doing all right. Just to finish off chapter 10 stuff, actually, I wanted to give you a top hat question on resonance. And remember, I'll just send it to your phones, I guess. The idea with resonance was that if there is a natural frequency of simple harmonic motion for a system, which there often is, and if you drive the system with a periodic force whose amplitude varies with the same frequency as that natural frequency, then you get a very high amplitude. So here we've plotted amplitude versus the driving frequency. And when the driving frequency matches F sub 0, so F sub 0 is sort of what you found before. It's 1 over T is the natural frequency for simple harmonic motion. SHM being simple harmonic motion. So the top hat question here is saying, they're talking about washboard roads. So this is a resonance phenomenon, is that cars can bounce along, and they can, as the dust settles and a car goes past, it can naturally form patterns, which are these equally spaced bumps on the road. So if there are a bunch of equally spaced bumps on the road every 10 meters, and You have underdamped shock absorbers that have a natural vibration frequency of 0.9 hertz. What driving speed would you feel the bumps the most? This is, by the way, a chapter 10 problem. And I'll just draw kind of a little diagram here. So think about this. Think you get what I'm getting at, you can always share your answer with your neighbor. Okay, should we discuss this one? Survey says. So thanks for clicking in on that. I had, curious as to how many actual, so 179 of you said 9 meters per second. So I liked it. There are a few different ways of doing this, but my idea is that for resonance, if this is V is d over t, if it's going at a constant speed, I guess, then the t there would be this t0, which is 1 over the frequency. So I could say V is equal to d, this distance, divided by t0. That's d times 1 over t0. That's d times the frequency. So I would just say 10 meters times that normal frequency of your car. So V is 9 meters per second. Okay. And I think that kind of gets through chapter 10 stuff. A few things from the pre-course or pre-class survey this morning. One was actually about this problem set, which is due this weekend. Can we solve question 1 in the problem set using the period of simple harmonic motion? So I think you got it. I think that's the idea. A bounce is half of a simple harmonic motion period. And I think it's the only way to solve this problem, because as this mass hits the spring, the force is changing with distance linearly, but it's not changing with time linearly. I think it's some sort of cosine or something, or a sine function. And I just don't know how you're going to be able to solve this in any way other than when it is touching the spring and being pushed by the spring, it should behave like a simple harmonic motion oscillator. So this is going to be half the period to get there and back. That's the way I would do it. Somebody asked, are hertz and 1 over seconds the same unit? That's definitely right. We just noticed that actually in that bumpy example with the washboard road. And then someone asked, again, if there's going to be will there be an optional problem set for chapter 11? Yes, there will be, and I'm hoping to post that later today. I'll put it under that module for practical 9. Happy birthday, Anahita. I'm not sure, you filled out the pre-class survey a bit early, but there's a wave. So last time I asked, 2 of the 5 senses depend on waves to work. Which 2? So that's sight and sound. Sound is a pressure wave which travels through the air, and light is a wave in electric and magnetic fields. So we're into chapter 11, which is called mechanical waves. So a vibration is a periodic motion of a particle around some equilibrium position. That was chapter 10. Now, what you can have is if you have many particles next to each other and they can all vibrate, then you can have energy traveling through the medium or past all these particles from one place to another, going a distance now. So the idea was that in chapter 10 you have one particle that is oscillating around an equilibrium position with simple harmonic motion. And so really it's just its position is a function of time. But now with a wave you have lots of particles that are vibrating with time, but you also now have the wave has some distance to it. It goes in maybe along the x-axis or something, and it's vibrating in the y-axis. So now you have two independent variables. It's time still, but also position. So the equations look similar, but a little more complicated, because they have now x and t instead of just t. Example will be water waves. They're showing a little example there. Light, which is an electromagnetic wave, and sound. And somebody asked me this morning, do I think that light is a wave or a particle? That's a really good question. This is to do with the wave-particle duality of light. So one way of answering this, I'll kind of skirt the question and say that light is light, and a particle model of light or a wave model of light can be applied depending on what it is you're observing about the light. So for this course and for physics 132 is what I meant to say there, is you should think of it as a wave, I think. Certainly, it's definitely true that light has a wavelength and a frequency, and it'll diffract around edges and has wave fronts and everything, so it certainly behaves like a wave, especially when it travels from one place to another. However, when it gets to a screen or something, it always arrives in these little localized bundles called photons. So, and I think that the chemists tend to think of light as this stream of particles because every time an electron is bumped from one orbit to another or excited in some way, it only takes energy from the light in these bundles of energy with a certain amount given by the frequency. It's Planck's constant times the frequency gives the energy that that actual matter can receive from that light. So that's the wave-particle duality. And then what's also even worse is that not just light travels like this, but even particles like a stream of electrons turns out also travels like a wave and will diffract and have a wavelength and a frequency or a helium nuclei or anything. So it's not just light that has a wave-particle duality, it's absolutely everything. So, and that's called quantum mechanics. Well, we're just going to talk about waves today. That's what the chapter 11 is all about. Here's a kitty, and the idea here is that when an object vibrates, it disturbs the medium surrounding it. So this cat's tongue is touching the surface of the water and creating these little ripples, which then travel out through the medium. And here they show a beach ball kind of landing. If it vibrates down and up once, then there is kind of a wave which goes out in these circles, and if you look at it from the side, you see a little bump there. So what these are is two-dimensional, what are called wave fronts. And what a wave front is it's the crest in a wave. Circular wave fronts. It can be a little hard to picture this, and we're not going to spend a lot of time actually studying two-dimensional waves, so I tend to kind of skip it and go right on to the three-dimensional waves. So what's going on here is that there's a source, a point source, that's producing spherical sound waves, which are alternating compressions and rarefactions of air. So if you make a plot here of maybe, I don't know, pressure or something, or density versus distance, what you'll see is that it'll go up and down like that. So I don't know what we're plotting here. Maybe pressure. Pressure versus, you can either plot pressure, or you can plot density, or you can even plot the position of particles relative to their equilibrium position. But most people talk about sound as a pressure wave. So the pressure goes up and then down and up and down. And so these are little crests. They move away from the source. And then you could do the same thing, I guess, for the y-axis. Negative, positive, negative, positive, negative, positive. And so, and all these little crests go along the y direction, I guess along the z direction too. A little harder to draw it. Any direction that you plot, any radial direction, you're going to see that the pressure goes up, pressure goes down, pressure goes up, pressure goes down. And if you connect all of the maximum pressures, I guess the locus of all the crest points, that is called a wave front. That's what a wave front is. And so here we have spherical wave fronts that are concentric spheres all centered on the source and all expanding out at 340 meters per second. That's what a sound source is. Okay. And you could do the same thing. Instead of plotting pressure, you could plot electric field strength or magnetic field strength, and then you would have maybe a light bulb at the center, and now you'd have these wave fronts of maximum electric field strength spreading out. Except this now goes at 300,000 kilometers per second, but that would be how light travels out away from a point source of light. Okay. So these, what I've drawn here is pressure, but the particles in the medium are actually moving around in a mechanical wave. So this is a question about, from the survey this morning, can you explain the main differences between transverse and longitudinal waves in terms of particle motion and relative to the direction of wave propagation? So we're going to go through this a couple times, but basically it's just this. Transverse means the particles vibrate perpendicular to the direction of wave propagation. And when we did the wave in Con Hall, I think that was a transverse wave. Because if you think of it, I saw the wave go from here all the way around the room to there. So that's a horizontal velocity of the energy of the wave or something. But when it went by you, you just went like this, whoa, and then you sat back down. So your motion as a particle was perpendicular to the motion that the wave actually traveled. So the wave is a transverse wave. Longitudinal just means that the particles vibrate parallel to the direction of wave propagation. So let's try this. This one you don't have to stand up or sit down for. But let's try to do the wave in Con Hall. We'll do the longitudinal wave. So instead of going like this, whoa, what I want you to do is this. Whoa. Just sort of shift left and right if you can. And we're going to start with you people, sort of on this side of the road. I'm going to count to 3 and try to shake longitudinally if you can. 1, 2, 3, and say, whoa. Whoa. You got to say whoa or it doesn't work. Okay, there you go. Okay, so that's called a longitudinal wave. This is a pretty good try. It's a harder one to do. They don't do it at the Rogers Center. And some examples in nature, a wave on a string. A string is a transverse wave. And we can actually, let's do a demo of one of these. I don't know if you guys saw these little sticks. This is a transverse wave here. I can shake one end of it and sort of send a wave along. So what it is a bunch of bars that are connected by this torsion wire in the middle. And we could send maybe a couple of sine waves along like that. We could do a low frequency oscillation, kind of like that. And then it sort of spreads out in a big wave. I can try to flatten it a little bit. We can also do a high frequency oscillation from this end. And you get these tiny little waves. So that's one of the things that happens, is that if you increase the frequency, then the wavelength of the waves decreases a bit. But what's interesting is that, kind of like this wave, nothing really moves sideways, but certainly the energy moves. Like if I wanted to high five my own self, I could hit it here, and boom. So somehow I've transferred energy from one part of the medium to another part of the medium without anything moving. It's just the energy that moves. So if I'm talking to you, there's some sort of vibration in my vocal cords, and then that energy propagates out through the air in the room, and then it vibrates your eardrum, and that requires energy. So the energy has gone from my vocal cords to your eardrum, and it carries information along with it, or high fives. So that's pretty good. Okay. We're going through a lot of concepts today, so that's the idea. Transverse wave, medium vibrates perpendicularly to the direction of energy transfer. And it's pretty easy to picture it. Longitudinal waves are a bit harder to picture. The medium vibrates parallel to the direction of energy transfer. And it is often accompanied, I guess it's always accompanied by what are called compressions and rarefactions. So an example would be a sound wave in a fluid. So what we're plotting here, sound is a longitudinal wave. Compression regions and the rarefactions travel at the speed of sound. In a compression region, the density and pressure of the air is higher than the average density and pressure. So we're in a medium right now with some particular like ambient pressure. If a sound wave's going through it, then the pressure is a little higher or a little lower. And that's, so this would be like a speaker. And then in here is air, not to scale, but this is like in a column, in a pipe, I guess. So this chapter talks a lot about these pipes of air that can be open or closed at the ends, and you can sort of see sound traveling through it in a particular line. So do you sort of see you have to almost blur your eyes, but you can see a region of compression traveling from left to right. And then there are these sort of vertical stripes. And then in between them, there's regions they're called rarefactions, where the density is lower. So the density is higher, lower, and those fronts move from left to right here. But if you look at any individual particle, it's just oscillating back and forth, left to right, as that wave passes it. So we'll do a top hat. I'll review also what this morning. These are pretty straightforward. Just take a minute. In a longitudinal wave, the vibrational motion of the particles is parallel to the direction of the propagation of the disturbance. So what's a transverse? 60 seconds to click in on that. Check your neighbor. Sort of like another synonym for the word perpendicular is transverse. We also had normal, right? Like normal is when you're talking about a surface. Anyways, okay, moving on. Yeah, so there is this whole business of snapshot graphs versus history graphs. So the idea here is that you have a particular wave that's traveling along, and this is a transverse wave, but instead of going up and down, we just send one pulse. You can imagine that, right? I just whip a pulse along. Well, what you've got, so I can do it with the rubber hose really quick, just to sort of show you. What you've got now is two spatial directions, X and Y. So Y is that vibration direction of the particles, and X is the direction that the wave propagates. So if I want to send a single pulse, I just go like that, and off it goes. Oh, even reflected. You can't see it. So that's what this is. So I oscillate this up and then off goes the pulse. Okay. So now we have time and X. So if we take a snapshot, like a photo of the wave as it's traveling along, that's called a snapshot graph, because what we're plotting is Y versus X. But we're freezing it for a particular instant of time. So it's literally a picture of the wave at this instant. And it's pretty easy to to understand, I think, what a snapshot graph is. So now I'm going to try to build up what's called a history graph. So here's the idea. Let's say we put a little piece of tape on the rubber hose at a particular position and took our stopwatch and measured the y position versus time for that particle. So what we would do is look at different instants of time, and we'd see that snapshot going from left to right. Okay, so what would happen to the particle here at position x1 is it would quickly go up, and then after some time later, it would go down. And we can take all those times and plot it out, and that would be a history graph. And it looks like this. So this is time, and you can tick along here. This might be, what was it here? I think at there it is. At T1, it was just going up a little above. And then at T2, it had gone over the hump. So this is maybe T1. And then it had gone over the hump, so that's T2. And then I'm just plotting all these things from here. T2, T3 is it's almost at the end, and then T4 is it's gone past. So T3, and then T4 is here, I think. So these are the like seconds or something. I don't know what exact units are. Maybe they're milliseconds or something. But what's interesting is that, so this graph tells the history of that particular point in the medium. And what's sort of weird too is that if the wave is moving from left to right, the shape of the history graph is reversed compared to the snapshot graph. So I don't know if you noticed that, but when we sent the pulse and took a snapshot, the steep side was on the right and the shallower side was on the left. And now it's flipped when you do the history graph. So that's, but to get sort of what's going on here. So we have two dependent variables, x and t. And so, two independent variables, x and t, and the dependent variable is y. So we can make up, I can't make a 3D plot, so I can plot either y versus x, that's called a snapshot graph, or I can plot y versus t, and then that's a history graph. All right, let's see if you can do it. It's always easier to listen to someone talk about it than actually try doing it. So, and you get more out of trying it yourself. So I don't know if this came up in your phone very well, but there's 4 graphs to look at. One is the history graph. So I'm giving you a history graph, and now I'm saying, okay, the figure shows the history graph of the left end of a 12-meter long rope. So the x equals 0 position. Left end meaning that x equals 0. And then they give you that the wave velocity on the rope is 2 meters per second. So it's moving from left to right at 2 meters per second from the 0 towards the 12. And which graph below correctly shows a snapshot graph of the wave at a time t equals 5 seconds. And I haven't even given you the 5th second here, but this is we know that at time 0 is when we start that pulse on the left end, and then at 3 seconds we've ended the pulse with a quick downward motion. You guys gonna get it? This is showing what I do to the left end with the history graph, and at 5 seconds, where do you expect the snapshot to look like? A lot of you are voting for D. That's the one I picked as well, but let's go through the reasoning of this. So, first of all, the what do we do first? So first we do the leading edge, right? I guess so I would say that the leading edge which is shallow, is at x equals 0 at time t equals 0 seconds. Okay, and so I would say at t equals 5 seconds, this should have traveled. D is equal to v times t, so it's 2 times 5, 10 meters. So it should be out at 10 meters. That's one thing. The other thing is that this comes later, so the trailing edge is steeper. So what I am going to do, if I do this thing, I go up slowly at time t equals 0, and then I whip it down at time t equals 3, I'm going to produce a pulse that travels along at a speed of 2 meters per second towards the right. And I think it should end up kind of here. The other thing I guess we could try to figure out, this is 4, this is 6 meters long. Does that seem right? The whole pulse took 3 seconds to, like a time interval of 3 seconds. If it's going at 2 meters per second, we would expect a pulse that's 6 meters wide, right? So that's also good. So it has to be flipped, so it can't be this one or this one, not flipped. Right? It's got the trailing and leading edges wrong. Similarly for this one, not flipped. It's also not 6 meters wide. And the problem with C is just that it's in the wrong position here. I'd expect it to have gone a lot farther by t equals 5 seconds. Okay. Hasn't traveled far enough. It's the right shape. So this is probably what it was like at maybe 3 seconds, right? How you guys doing with this? Okay. So that's wave pulses. I think what we're going to do next is do more of a continuous kind of sinusoidal wave. So you can shake the end any way you want. You can make the pulses like this. You can make it in a square shape. You could, oscillate it in a sinusoidal like a motion. And that's what we're going to do. So cosine is one possible shape that a wave can have. And there they are. But anyway, so there's a bunch of different things. There's T. Capital T is the period of the wave. It's the time to complete one vibration of a point in the medium anywhere along the wave's path. The frequency, F is just 1 over the T. Sometimes people talk about the frequency of a wave. It's important. The amplitude comes out in front of the cosine function. It's just how high in the y direction the wave is. Or for a sound wave, the amplitude could be measured in units of pressure even. And then the wave speed, v, comes in there somewhere. It isn't actually here. So it turns out that v is equal to lambda divided by t. It's a good one to have on the H sheet there. So many different ways of representing this, but the one from the book kind of looks like this. Y is a times cosine of blah, blah, blah. But so what I'm showing here is now the velocities of the particles that are on the wave. So I have a top hat question for this. I'll start this question. Shown is a snapshot graph of a wave on a string with velocity vectors showing the velocity of the string, the particles in the string at various points. As the wave moves along x, the velocity of a particle on the string is in the y direction. So this is about the amplitude. That was this morning's quiz, amplitude. Oop. Is there a simpler form to represent the complicated formula of a sinusoidal wave? Somebody asked this morning. And a little bit. So this is the equation that Akina gives. But if you want, you could define some new variables. Wave number is sometimes what people call 2 pi over lambda. Sometimes people use omega for 2 pi over period, and you get it looking a little like this. My issue is that there's like square brackets of the cos, and then there's nestled round brackets in there, and there's a ton of fractions and stuff. So it looks pretty nasty looking. The reason I don't like this equation is because there's new variables here that are also kind of confusing. Omega is not the frequency, it's 2 pi times the frequency, and k is not the spring constant, it's something, it's just 2 pi over the wavelength. So anyway, this is the top hat question you're seeing right now, and it's just asking you for, you got a sinusoidal wave, it's moving from left to right. What's the direction of the velocity of this point that's the circle right there? Got it? Okay, this was a hard one, actually. But let's see what people answered. Hey, nice work. Okay, so hopefully, so it looks like a lot of you got that it was either up or down. And it's a transverse wave, so that's the idea. The particles, just like as the wave travels past you, the particles are only oscillating up and down. And in fact, they're oscillating with simple harmonic motion, which is kind of interesting. So that's a bit of a link between chapter 10 and chapter 11, is that the particles in the medium, as a sinusoidal wave travels by, are oscillating with simple harmonic motion. So is it up or down? I thought it was up, and that's the tricky part. So the way that I do this is, so first of all, I know it's a transverse wave, so the particles have to have their velocity up or down. So, how do you figure it out? The way I think of it is it's like a pattern that is moving from left to right. So it's the pattern that moves, and then what the particles do is they run up and down to try to stay in the pattern. So let me show you what I mean. There's the pattern. So I've sent a wave along, and you can imagine this whole pattern moving from left to right. But it looks like something's moving from left to right, but nothing's moving from left to right. What's happening is just every particle it's oscillating up or down. If you can believe me, you believe me? So what's going to happen is that this is like now. So what I'm going to draw, let's choose a different color, maybe purple, we'll do later. So what's later going to look like? Well, it's going to go this way, right? You have to kind of draw this out. So to be later, which way is this particle going to have to go to get on to later? He has to go up, right? So to be on the pattern, does that make sense? Hopefully you've all figured it out in your own way, but that was the way I thought about it, is that this guy, the dot, has to stay on the pattern, and so if he wants to get there, to get to the purple curve, he's going to have to go up. So his velocity must be up at that instant. Okay. And what time is it? Yeah, we're pretty good here. We're doing great. I wanted to answer a question that was getting in about this, why is it flipped? Remember this whole thing? So what I was thinking is that this history graph is a very different thing than the snapshot graph. The snapshot graph is just a photo, and it shows that this leading edge, the steep edge, is on the right because that's the shape of it. But it's moving from left to right. So if you're standing there with a stopwatch and you're measuring the time, you're going to first get hit with the leading edge, and you're going to record that on your history graph. And then later, you're going to get hit with the trailing edge, and you're going to record that in your history graph. So if you put things on a y versus t graph, it's going to flip it. Because earlier times are on the left and later times are on the right. That's a good question. Okay, what else are we doing here? We're almost done the slides here. We got, oh yeah, so wave speed. There's an equation for wave speed. This is showing 5 snapshots. This is figure 11.8 from your text, showing this thingy moving from left to right. So these are a bunch of snapshot graphs. E says that the pattern has repeated. What's interesting is that E and A are the same. So it's gone. This crest has moved an entire wavelength, and it's taken a period t. So this is that equation I tried to write down before. The wavelength and the period and the wave speed can all be related. So if you have 2 of these, you can find the third. So that's if you have a sinusoidal wave. The wave speed is determined by the properties of the medium. So I'll write that down right here. The wave speed is determined the properties of the medium through which the wave travels. So, example, if you have a string that is stretched with a tension F, then the wave speed is the square root of F over mu, where mu is the string's mass to length ratio, also called the linear density. So we've got a bunch of new stuff here. F, I use F for tension, so that in newtons, because I don't want to use capital T, because now we're using that for period. T stands for period in seconds in this chapter. But it's tension. Okay. So you pull a string like that rubber hose, it has a tension. I increase the tension, then the wave speed increases. Also, it has a linear density, mu. And so if I increase the density, then the wave speed decreases. And if a wave is bouncing back and forth, it'll have a certain frequency. And this can happen on your guitar. So if you pluck your guitar, those waves will go back and forth at a certain frequency and you'll hear a note. And if you increase the tension, cranking it up, it'll go back and forth faster and you'll hear a higher frequency. Also, if you have a thicker string, then you'll have a lower frequency for the same tension. Which is why the lower notes on your guitar strings, they have you can see all these little coils. It's a thicker string. Slows it down. Somebody asked this morning, since the wave speed is equal to the square root of the force divided by the line density, is it true the wave speed is mainly determined by the density of the medium? So exactly. So it's always the properties of the medium that determine the wave speed, not the properties of the wave, such as the frequency and amplitude of the wave. The way I think of that is that it doesn't matter if you sing high-pitched or low-pitched or loud or quiet, the speed of sound is always 340 meters per second. And then there was this question where you actually use that equation. So the idea here is that the cable has a mass of 0.1 kilograms and a length of 10 meters, so mu is equal to 0.1 divided by 10 kilograms per meter, which is 0.01. And then the speed is equal to the square root of the force, the tension, divided by mu. So it's the square root of 100 divided by 0.01. And I think you get, we use the square root of 10,000. So you get 100 meters per second. Surprising that the units work out there. Before a class on Friday, we're going to keep going with intensity and reflection of waves. Basically, you're going to talk a lot about intensity, and then when we come back on Monday, we'll talk more about frequency. Okay, take care. See you Friday.